Okay. Hi. Thank you for having me here. I am Roberta Caruso from the Oxide MD group at the Brookhaven National Lab. So there's been a slight change with respect to the title that you can read in the program book. And so today, I'm going to talk about the effects of electrolyte gating on overdoped lanthanum strontium copper oxide. So this work I'm going to present is being carried on by myself together with my colleagues Anthony Bollinger, CA, and Ivan Bozovic. So the motivation, first slide, let me give you an overview of the motivation of this work. The scope of this experiment is the study of the overdope regime of LSCO, and in particular, we want to focus on the role of disorder in the superconducting transition. On the overdoped side, the critical temperature decreases with increased doping, and surprisingly, this also happened to the superfluid density, which also scales with the critical temperature. One of the possible explanations to this phenomenon is the dirty BCS scenario, where the demise of the superfluid density with doping is attributed to an increased pair breaking, which is caused by the induced disorder due to the increased dopant density. So you increase the dopant density, you create more disorder, and you increase the pair breaking, and so you diminish DC. However, the experimental results that I'm going to present in this work, confute this scenario. So in traditional experiments with cuprates, you change the whole doping by adding or substituting elements into the parent compound, or by changing the oxygen content through annealing. However, one may think of using some kind of electric field effect to tune the carrier density in more or less the same way you do with semiconducting materials, or in the same way you do with LAO-STO interfaces, for instance. The problem is that the traditional electric field gating does not modulate the carrier density enough to induce a significant change in the superconducting properties of the cuprates. So what we do, we use electrochemical means to tune the whole density by adding or remove dopants. So in this specific experiment, we start with a certain doping in the overdope regime. And then what we try to do is we increase the old doping to observe a decrease in TC, and then we reverse the process and decrease the whole doping to see an increase in TC. And so this technique allows us to study how the disorder is affecting the superconducting transition in overdoped LSCO. The technique that we use, the electrolyte gating, it's not entirely analog to a standard capacitive gating, but it constitutes a very powerful technique to tune the carrier density in cuprates, and also possibly in other materials with larger carrier concentration. So in this technique, an ionic liquid or a polymer with solvated ions is used as a dielectric between the sample and the gate electrode. So when a positive gate voltage is applied to the electrode, the positive ions are electrostatically absorbed on the surface of the film, forming an electrical double layer with the electronic charges are in the film. And an equal amount, of course, of oppositely charged ions accumulates next to the gate electrode. The electrolyte gating allows to reach has several advantages. So as I was mentioning before, it allows to reach the electric fields and the carrier concentration that we need to effectively dope cuprates. but it has also extended charging times, which are typically of the order of several minutes. And most importantly, the charge injection is at least partially due to some kind of electrochemical modifications. The sample that we study in this experiment is 18-unit cell LCO film with the nominal content of strontium of 28% deposited on a LSCO substrate. So the film surface is patterned into 6 hole bars with different width, ranging from 10 micrometers to 500 micrometers. And the area of interest is covered with an ionic liquid and is surrounded by a gate electrode, which is kept at a given voltage. When a gate voltage is applied, the charges accumulate on the electrode and opposite sign charges accumulate on the sample. In this way, a capacitor is formed between the layer of charges on top of the sample and the opposite sign charges that accumulate in the sample correspondingly. Now, these are some of the experimental results. The graph that you see on the left shows the resistance versus temperature curves for different gate voltages for the 20 micrometer device, while the one on the right shows the same curves, but for the 10 micrometers device in 2 different measurements run. Similar results have been obtained for all other devices on the sample. What we can see from this curve is that the resistance remains almost unchanged in the entire temperature range when the gate voltage is negative, and the same thing happens for the critical temperature. So when the gate voltage is negative, TC is basically unaffected, and at the same time, the R versus T curve is also basically unaffected. Then, when we go above a certain gate voltage value, which is a positive gate voltage value, the critical temperature increases dramatically. And at the same time, the resistance increases dramatically as well in the entire temperature range. The curves here are up to 45 Kelvin for clarity, but the R versus T curve is a straight line up to room temperature. In order to visualize better what I just said, we plot the critical temperature and the room temperature resistance as a function of applied gate voltage for the same 2 samples. So these data are extrapolated from the curves that I showed you before. Both quantities change very little for negative gate voltages. And then when we hit positive gate voltages, the increase is roughly exponential. Now, to interpret this behavior, we plot the residual resistivity ratio versus hole doping. So residual resistivity ratio, RRR, is defined as the ratio between resistivity at room temperature and the extrapolated resistivity at 0 temperature. The plots here are for the 10 micrometers device, 20 micrometers device, and 50 micrometers device. The residual resistivity ratio is a common way to have a qualitative measure of the quality of the sample in terms of defects, impurities, and generally speaking, disorder. So a larger RRR indicates a lower concentration of defects and impurities, and so a less disordered state. In our experiment, this quantity RRR increases as the doping increases, and so it indicates that there is a less disordered state. At the same time, the critical temperature decreases as the doping increases. So this is an indication that the disorder that is caused by hole doping is not playing a significant role in determining the temperature of the superconducting transition. The behavior that I just discussed only takes place in a certain applied gate voltage range. So in the first run, graph on the left, the gate voltage is ramped from negative values up to a certain positive threshold value. And above this threshold value, you see that the resistance changed dramatically. The critical temperature also changes dramatically. Actually, the superconducting transition is not complete. Then, when you ramp down the gate voltage down to negative values in run 2, so graph on the right, a completely different behavior is obtained, where we observe that the critical temperature is increasing as the gate voltage decreases, and at the same time, the room temperature resistance decreases. This is more or less the opposite of what we observe when ramping gate voltage from negative to positive value up to a certain threshold value. Finally, after a sufficiently large negative voltage is applied, the resistance versus temperature curves start to overlap. The critical temperature returns to the initial value. It's here. When the negative gate voltage hits a certain value, then the initial behavior is restored. And the conclusion would be that above, in this case, a gate voltage of 1.5 volts, some dramatic chemical and or structural modifications occur, sharply increasing the disorder level. Now, it's clear to see from these other plots that the effect is reversible in the sense that Tc is fully restored, as you can see in the top left graph. However, the residual resistance ratio remains consistently lower, as you can see in the bottom right graph. These partially reversible changes in RRR indicate that there is some irreversible electrochemical doping, which is due to the ionic liquid. It is reasonable to assume that these changes contribute to the overall disorder of the material, because as you can see, the RRR remains lower. However, Tc is unaffected by these changes in disorder, and so this supports our initial assumption that disorder is not playing a significant role in the superconducting transition. So, in conclusion, what I was trying to show with this talk, with this experiment, we have demonstrated that we can tune the critical temperature of overdoped LSCO by means of electrolyte gating. And in doing so, we observe that as doping is increased, both the critical temperature and the residual resistance ratio decrease. We also observe that the disorder, which is qualitatively measured as the residual resistance ratio, is a multi-valued function of the critical temperature, as you can see in the bottom right graph. These two observations support the conclusion that disorder plays a marginal role in the observed critical temperature reduction of the overdoped regime when the whole doping is increased. I'm leaving you with the summary slide to summarize the important message, the take-home message of this talk. So the experimentally observed demise in Tc with the doping cannot be explained by an increased pair breaking due to the increase in dopant density and the resulting disorder. This scenario is in fact refuted by these direct and simple experimental facts we have just shown you. And that's the end of my talk.
Thank you for being on time. Questions? We still have a couple minutes for questions before we have the break. Okay.
Hi, thank you for the talk. I mean, there are many types of different disorder, and not all the disorder will affect things in the same way. So, do you know which kind of disorder you are creating in these films?
It's not an easy question to answer, especially because from transport measurements, it's not really easy to tell what kind of disorder we are creating. So for sure, we know that we are increasing the carrier concentration. We also know from other measurements and previous work that we are somehow electrochemically doping the devices. So there is a disorder caused by implantation of ions from the ionic liquid. But with this kind of measurements, this is pretty much all we can say about disorder, the type of disorder that we create.